Welcome again. In 1865, the German organic chemist August Kekule proposed this structure for the molecule C6H6 with molecular mass 78, benzene. At the time, this was considered an excellent explanation for the structure of this molecule. But since that time, we realized that the structure of benzene is best represented in this way, with the sp2 hybrid orbitals of each carbon, giving rise to a delocalized system where the electrons are shared among all 6 carbons. And this system is best represented by the circle. But where is the evidence for such a structure? Let's consider first some chemical evidence. Cyclohexene with 1 point of unsaturation in a 6-membered ring. The enthalpy of hydrogenation is negative 120 kilojoules per mole. If another point of unsaturation or another double bond is added to this 6-membered ring, then the enthalpy of hydrogenation is approximately twice that for a single bond, a value of negative 231 kilojoules per mole. But consider benzene, which, if it did consist of 3 double bonds, as thought by Kekule, then we would expect approximately 350 kilojoules per mole in keeping with this trend. But in fact, the enthalpy of hydrogenation for benzene is negative 208.5, significantly less than we would expect from this data. And this lends support to the idea that the benzene molecule does not consist of 3 double bonds per se, but of a system of delocalized electrons. Another piece of chemical evidence can be had by looking at the addition and substitution reactions which are typical of alkanes and alkenes. Typical alkenes, which contain 1 point of unsaturation, decolorize bromine water, and in so doing they are said to undergo an addition reaction. In the case of benzene, however, this addition does not occur. Benzene is more likely to undergo this reaction, which is typical of alkanes. This is a substitution reaction where a chlorine free radical removes a hydrogen and takes its place. This provides us with chemical evidence to support the idea that benzene is best represented by this structure as opposed to this. And what about the physical evidence? Physical evidence can come from X-ray diffraction, where benzene molecules are crystallized and X-rays sent through the sample. The diffraction patterns that are produced can give us information about the bond length of benzene. And we notice here that the bond length, the carbon-to-carbon bonds in benzene, are 140 picometers in size. This is longer than a double bond, which has a size of 134 picometers, and less than a single bond, which has a size of 154 picometers. Other physical evidence can come from electrostatic potential mapping, which lends support to these bond lengths.